So the molar concentration of H plus and OH minus ion divided by the molar concentration of water. 298 Kelvin, and only at 298 Kelvin, the ionic product of water, that is Kw, will be equal to 10 to the power minus 14. So when the value of Ka is more, what happens? The strength of the acid also increases. So it is directly proportional, which is a very important equation. Ka into Kb will be equal to the ionic product of water. Hello everyone, this is Ambli Unnakrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in the last session, we discussed about Lewis theory of acids and bases, as well as some numericals based on equilibrium constant were also discussed in the last session, right? So in today's session, we are going to discuss about ionization of acids and bases, right? Dissociation constant of weak acids or ionization constant of acids, Ka, and dissociation constant or ionization constant of weak bases, which is called as Kb, and what are polybasic acids and what are polyacidic bases we are going to discuss, as well as the factors affecting acid strength and about pH of a solution also we are going to discuss in this session. Okay, so to begin with, ionization of acids and bases. So before studying about ionization of acids and bases and the ionization constant of acids and bases, first let's discuss about the ionic product of water. Okay, ionic product of water. So dissociation means what? First of all, when a molecule or a compound dissociate into its constituent ions, right? So water is considered as a weak electrolyte. So weak electrolyte means some amount of water gets dissociated into its constituent ions. That means water will get dissociated into H plus and OH minus ion, right? And it is a weak electrolyte means it is not getting completely dissociated into H plus and OH minus. So that is why you can see at the same time H plus and OH minus will combine and form back H2O. So that's why you can see a double arrow here, which shows that it is under equilibrium, right? So this is called as ionic equilibrium. So it is a weak electrolyte and it undergoes partial ionization and can be represented in this form. Okay, so this is what you can see from here. So now we are going to apply law of mass action, which we have already studied. So applying law of mass action, K will be equal to what it is, molar concentration of the products divided by molar concentration of the reactants raised to the power which is equal to their stoichiometric coefficient. So what are the products here? H plus and OH minus, right? So the molar concentration of H plus and OH minus ion divided by the molar concentration of water, right? Now we are going to take this concentration term to the other side of the equation. So it becomes a multiplication there, right? It was in the denominator here. If you take to the other side, it will come in the numerator. So K into molar concentration of water will be equal to molar concentration of H plus into OH minus. So this term K into molar concentration of water is called as the ionic product of water. That is Kw, which is called as ionic product of water, which is equal to the product of molar concentration of H plus and OH minus ion. So this is called as the ionic product of water, which is equal to the product of molar concentration of H plus and OH minus ion. So it states that ionic product of water is the product of molar concentration of hydrogen ion and hydroxyl ion in water or in any aqueous solution. So I hope what is ionic product of water is clear for you. And at 298 Kelvin, this is very important, at 298 Kelvin and only at 298 Kelvin, the ionic product of water, that is Kw, will be equal to 10 to the power minus 14. Also, we can also write it as, see, Kw is what? H plus into OH minus, molar concentration of that. So molar concentration of H plus into OH minus will be equal to 10 to the power minus 14 at 298 Kelvin. So in either of these way, we can represent. Okay. So I hope ionic product of water is clear for you. Now moving on to the next one, that is ionization of acids and bases. Now from this equation itself, Kw is equal to H plus into OH minus ion, molar concentration of H plus and OH minus ion. In acidic solution, what happens? Acidic solution means, of course, the concentration of H plus ions will be more, right? So in acidic solution, molar concentration of H plus ion will be more than OH minus ion. And in basic solution, molar concentration of OH minus ions will be greater than H plus. So what will happen in neutral solutions? The molar concentration of both will be equal, right? H plus ions and OH minus ions will be equal, which is equal to 10 to the power minus 7. Okay, so in a neutral solution, the concentration will be 10 to the power minus 7. Molar concentration of H plus and OH minus will be equal, which is equal to 10 to the power minus 7. Now we are going to study about the dissociation constant or ionization constant of a weak acid, which is represented by the symbol Ka. This small a stands for the acid and K is the ionization constant. Okay, so now we are going to consider a weak acid, which is Ha, ionized partially in water and which is represented by this given reaction. So Ha is the weak acid here, right, which dissociates into H plus and A minus ions, okay, which partially dissociates into H plus and A minus ion, and it is happening in presence of water. So that means Ha as well as water is present here. So what happens? This water will take up this H plus ion and form H3O plus and A minus, right, which is shown in this equation. So Ha, which is the weak acid, in presence of water forms H3O plus ion and A minus anion. So I hope it is clear. So again we are going to apply law of mass action here. So K will be equal to H3O plus, molar concentration of the products, right, H3O plus and A minus, divided by molar concentration of the weak acid and water, which is shown here. Now again we are going to take this term, that is molar concentration of water, to the other side. So we will get K into molar concentration of water, okay, which is equal to H3O plus into A minus divided by Ha. Okay, now K into molar concentration of water is called as the ionization constant or dissociation constant of weak acid, which is Ka. So what is Ka? It is equal to product of the molar concentration of H3O plus and A minus divided by the molar concentration of the weak acid. So I hope it is clear. So this is the equation for Ka of a weak acid, right? So Ka is defined as the ratio. It is the ratio of product of molar concentration of dissociated ions to the molar concentration of undissociated acid molecules at given temperature. So what does that mean? H3O plus and A minus are the dissociated ions, right? And from where it has dissociated? Ha, which is the undissociated acid, undissociated weak acid. So we can also define as the ratio of the concentration or molar concentration of the dissociated ions to the molar concentration of the undissociated acid. So these things are dissociated, right? And this is the one which is undissociated. So it is a ratio of product of molar concentration of dissociated ions to the undissociated acid molecules. Okay, it shows that larger the value of Ka, okay, when the value of Ka is large, the stronger will be the acid, and smaller the value of Ka, weaker will be the acid. So when the value of Ka is more, what happens? The strength of the acid also increases. So it is directly proportional. When the value of Ka is more, strength of the acid will be more. The acid will be a more strong acid, right? Now moving on to dissociation constant or ionization constant for a weak base. Okay, for a base we are going to consider now. So BOH, let it be the base, and in presence of water it forms B plus and OH minus ions. So these are the dissociated ions and this is the undissociated what? Weak base, right? Now again we are going to apply the law of mass action. What we will get? K will be equal to molar concentration of these two, B plus into OH minus divided by molar concentration of BOH, which is the weak base, into water. Again we are going to take the water to the other side. So you will get K into molar concentration of water will be equal to whatever is left here, B plus OH minus and BOH. Now what is K into molar concentration of water? It will be Kb, right? That is dissociation constant or ionization constant of a weak base, Kb. So it will be molar concentration of B plus into OH minus divided by BOH. So in the same way how we have defined the ionization constant of acid, the same way we can define it here also. It is the ratio of, yes, how we have defined in the case of dissociation constant of a weak acid, the same way we can define the ionization constant of a weak base as well. So Kb is defined as the ratio of product of molar concentration of dissociated ions to the molar concentration of undissociated base molecules at given temperature. Right, this is the dissociated ions. So it is the ratio of the product of molar concentration of the dissociated ions to the ratio of molar concentration of the undissociated weak base. So I hope it is clear. Now it shows that again in the same way, larger the value of Kb, stronger will be the base, and smaller the value of Kb, weaker will be the base. So I hope it is clear. Again in the same way, when the value of Kb is more, strength of base will be more, and when the value of Ka is more, strength of acid will be more. Okay. Now we are going to see the relationship between Ka and Kb, that is ionization constant for a weak base and weak acid, that is, which is a very important equation. Ka into Kb will be equal to the ionic product of water. Ka into Kb will be equal to Kw, or else Ka into Kb is equal to Kw, which is equal to, we know already the value for Kw, which is 10 to the power minus 14 at 298 Kelvin. So at 298 Kelvin, Ka into Kb will be what? 10 to the power minus 14. Okay. So at 298 Kelvin only that value, that is Ka into Kb will be what? 10 to the power minus 14. So I hope it is clear. So this is Ka and Kb. Now moving on to the next concept, that is polybasic acids and polyacidic bases. So we have already studied in the previous session about basicity of acids and acidity of bases, right? So now in the same way we are going to see what is a polybasic acid and what is a polyacidic base. Okay. So from poly word itself you can say something is many or in many amounts is present there. So let's see. Polybasic acids are acids which can donate more than one H plus ion. So polybasic acids. So acids means what? Which can donate H plus ions, right? So polybasic acids means which can donate more than one H plus ions. Then what will be polyacidic bases? Bases means which can donate OH minus ions, right? Are bases which can donate more than one OH minus ion. Okay. So these are few examples of polybasic acids. So let's consider the first one, H3PO4, which is orthophosphoric acid. So in this case you can say 1, 2 and 3. 3 hydrogen atoms or 3 H plus ions can be donated. So we can call this as a tribasic acid. How many H plus ions can be donated? 1, 2 and 3. Now the next one is H3PO3, that is orthophosphorus acid. H3PO3. So now in this case this hydrogen atom is directly attached to the phosphorus. So this hydrogen atom is not ready to be replaced or it is not ready to be donated. So how many are there? This one hydrogen atom and this one hydrogen atom. So there are 2 H plus ions which can be donated. So this is a dibasic acid, 1 and 2. Okay. Now the next one is H3PO2, that is hypophosphorus acid. So in this case also these 2 hydrogen atoms are directly attached to the phosphorus. So this won't be able to be donated. So now only one hydrogen is present. So this is a monobasic acid. So I hope it is clear. So this is called as the polybasic acids. I hope it is clear. Now in polybasic acids, Ka1, Ka2 and Ka3 are the first ionization constant, second ionization constant and third ionization constant respectively. But Ka1 is greater than Ka2 is greater than Ka3 because it is more difficult to remove proton from a negative ion due to electrostatic force of attraction. So what does that mean? So from here itself we have discussed what happens. Yes, polybasic acid means it is ready to donate one H plus ion. So when it is donating one H plus ion, it becomes a negatively charged species, right? Yes. So for example, if you are taking HA, it is donating one H plus ion means it becomes HA minus, right? It is donating its proton. So what happens in that case? It becomes a negatively charged ion, and because of the electrostatic force of attraction, what happens? It becomes more difficult to remove another H plus ion from it. Hence, Ka1, if it's the first ionization constant, means first H plus ion is removed. Ka2 means second H plus ion is removed and Ka3 means third H plus ion is removed. So in that case, Ka1 will be the highest because it is difficult as we keep on removing H plus ion, the negative charge increases, electrostatic force increases. Hence, it becomes more difficult to remove the H plus ion. So, I hope this order is also clear for you. Hence, what happens if we are considering HA will be strongest, then HA minus and then A minus. Okay, so as we keep on removing the hydrogen or H plus ions, it becomes more difficult to remove it. Okay, so I hope it is clear. Now moving on to the different factors affecting the strength of the acid. So the first one is bond strength or size. So as the size of the elements increases down a group, bond strength decreases, so acid strength increases. So we can also talk it in term of bond length as well. So if we are considering in this case itself HF, HCl, HBr and HI, right? So that is fluorine, chlorine, bromine, iodine. So as we move down the group, what happens to the size of these atoms? It will become bigger and bigger, right? So if I am drawing H and F, let this be H and let this be F. This will be the bond length, okay? And as we move down the group, what happens if I am considering for H and I will be big one, right? As we move down the group, the size of the atom increases. So what happens? Of course, the bond length increases. As the size of the atom increases, the bond length also increases. So what happens when the bond length increases or the size of the atom increases? Yes, the electrostatic force of attraction decreases and it becomes easy to remove one electron or easy to remove a proton from it, right? As it is an acid, it should be ready to donate its H plus ions. So as its size becomes more, it is easy to remove the H plus ions. Hence, what happens? The acid strength also increases. So as the bond length increases or the bond size or the size of the atom increases, the acidic strength also increases. So I hope that point is clear for you. The next one is polarity or electronegativity. So as the electronegativity increases in the same row, polarity of the substance increases, therefore acid strength also increases. Okay, as the electronegativity increases, we already know which is the highest electronegative element. It is fluorine. So when the electronegativity increases, the polarity between the bond will be very high. So in that case, what happens? The acid strength increases. So in this case also CH4, NH3, H2O and HF. You can see it is carbon, nitrogen, oxygen and fluorine. So if you are comparing these four, fluorine is the one having highest electronegativity. So of course, which one will be the acid having highest strength? It will be HF. So you have to see the elements which is present, whichever is having the highest electronegativity, that will have the highest strength, okay? And in this case, whichever is having the highest size or bond length, that will have the highest acid strength. So I hope it is clear. Now moving on to the next one, that is pH of a solution. Okay, so you are already familiar with what is pH. It is used generally to calculate the acidity or basicity of a solution, right? Okay, so it is the negative logarithm to the base 10 of the molar concentration of H plus ion in a solution. Okay, so that is the equation to calculate pH. So you are already familiar with what is pH, right? For acidic substances, it will be less than 7. For basic substances, it will be more than 7. And if it is equal to 7, if the pH value is equal to 7, we say that the solution is a neutral solution, right? Okay, so the equation to calculate pH is minus logarithm of molar concentration of H plus. Okay, or else you can, as minus is present there, you can put it in the denominator also, as well as write as pH is equal to log to the base 10 1 by molar concentration of H plus. And pH scale ranges from 0 to 40. 0 to 7 it is acidic. The value, if it is less than 7, it is acidic. As we move towards 0, the acidity increases, right? And 7 to 14 is basic. As we move towards 14, the basicity will be more. And pH of blood, the value is very important. It is 7.35. So it is a slightly basic. I hope it is clear. Now, what is pOH of a solution? It is a negative logarithm to the base 10 of the molar concentration of hydroxyl ion. The same way as we have written pH, pOH will be minus log OH minus concentration, molar concentration of OH minus. And at 298 Kelvin, pH plus pOH will be equal to 14 in neutral compounds or neutral solution. Okay, so that means pH plus POH will be equal to 14. So if this is equal to 14, in neutral solution, what happens? pH will be equal to POH will be equal to 7. The value will be 7. That is why 7 plus 7 will give you 14. Okay. So this point is also very important. At 298 Kelvin, POH plus pH will be equal to 14. Okay. So in the next session, we are going to discuss how pH and POH will be equal to 14 and the further concepts regarding that. Okay. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.